We're looking at the exponential distribution in this video. So you are expected to have looked at lecture notes 10 and looked at the characteristics of the exponential distribution, the formulas that are involved, and so I'll just go through the formulations that are discussed in that that set of slides. You don't have to integrate the exponential function. That's basically what's going on here to find probabilities. But what's nice is for the exponential is it's pretty well set. So if you integrate the exponential function from x to 0, or from 0 to x, I'm sorry, then that's set as a certain formula that you would use. So whatever x happens to be, we can just plug into that particular formula. For greater than x, so x to infinity, there's a certain formula for that. And then between two values, a and b, let's say, there's a specific formula for that. So you don't have to go in and try to integrate the exponential function each time, depending on what the values of interest are. So we'll look at that, and then we'll look at how the exponential and the Poisson are related. And before we do that, just some uses of the exponential are often in dealing with waiting line models, lifetime of mechanical devices, things like that. That amount of the amount of space between flaws. Okay, so it's often on a time continuum or a space continuum, something like that. So you certainly have a continuous random variable there, time, for example, and in the exponential, then we are dealing with a continuous probability density function, or continuous random variable, which gives us a probability density function. And so the area under the curve that's produced from the characteristics that we have is equal to 1, and so we find portions of that area for the probability. So I gave you those resulting formulas that give us the probabilities. I gave those to you in the notes. Obviously, the area will depend on the formulas the same, but the area, the resulting area, will depend on. So, for example, between the area 0 and 0.2, let's say here, we would have to find this area here. Well, that would depend on whether the mean number of arrivals per time period is 4 or 1. Let's change this to 1. So now you're going to have a very different amount of area versus, let's say, 10. Okay, so that amount of area there. Okay, and so it certainly depends on what the average is. The average amount of time between arrivals is actually the reciprocal of this value here, the mean number of occurrences, of arrivals, of successes per time period or per space. Okay, let's go back to 4. Okay, and so if we know that the mean number of arrivals per minute, so let's say we're looking at the amount of time between arrivals at an emergency care facility, we're looking at it in terms of per minute. If we know that the average number of people who arrive per minute is 4, then we know that the amount of time between arrivals, the mean of that, is the reciprocal of 4, so 1 over 4, so 0.25. Okay, so it's just 1 over this lambda. Now, lambda is important because that's what's used in the formulas that we're going to use. Okay, so if we have the exponential mean, that's fine, but don't use it in the formulas here. Find lambda from that. So just take the reciprocal. Okay. So now, whether we're given 4 for the mean number of arrivals per minute, or we're given 0.25 for the average amount of time between arrivals, we then know that lambda is 4, and we can find probabilities such as what's the probability that 1.5 minutes or less will lapse between arrivals. So somebody has arrived, checked in. What's the probability that less than 1.5 minutes will go by before someone arrives again? Well, that's just the formula 1 minus e to the minus lambda minus 4 times x, 1.5. Okay, so 1 minus e to the minus lambda times 1.5. So the probability is pretty high, okay, that 1.5 or fewer minutes will lapse before the next person arrives. Okay, what's the probability more than 2 minutes will lapse before the next arrival? Well, that's basically 1 minus this less than or equal to here. And remember, there's really no difference in terms of probability. There's no difference between greater than x and greater than or equal to x. Certainly a difference in the statement themselves, but in terms of probability, there's no difference. So 1 minus all of this here gives us then e to the minus lambda x. So e to the minus 4 times 2 is pretty small, 0.003. So it's pretty unlikely that over 2 minutes will lapse before the next arrival. Okay, and then you've got the probability x is between 0.25, so 15 seconds, and 1 minute. Now, if this said 15 seconds and this said 1 minute, you have to do some rearranging here. You have to get this 2 minutes. So that's 0.25, okay, minutes. So make sure they're both in the same units as your lambda. Okay, so it's per minute here. So in this case, then, essentially what you're doing is you're finding the probability that x is greater than or equal to 0.25 right here, and then you're subtracting the probability x is greater than or equal to or greater than 1. Okay, so you're subtracting this a little bit here. So you're taking e to the minus lambda times 0.25 minus e to the minus lambda times 1. Okay, and so that's 0.3496. Okay, so the probability that between 15 seconds and 1 minute will lapse before the next arrival is about 0.35. And you can find those using the expon.dist command in Excel, where you have x as your first value, lambda, so not the mean of the exponential, but lambda, and then telling it whether you want cumulative, so you put true or 1 for the cumulative probability. The other option is not like in the discrete probability distributions for the Poisson and the binary, where you if you put false, you got the probability x was equal to some number. That can't happen for the continuous random variable. So if you put false or 0, then what you're going to get is this f of x. You're just going to get the height of the line at that particular value. Okay, and that has that doesn't give us probability at all, so we generally aren't dealing with that for continuous. All right, and so you can use so then for the greater than, you'd have 1 minus the cumulative. And this is a little confusing here because it's cumulative. You're dealing with cumulative. You're taking the largest cumulative minus the smallest cumulative. Okay, whereas here we were doing greater than or equal to minus greater than or equal to, so we were actually starting with the smallest value minus then the largest x value. So these are a little bit different, but they're just mathematically they're getting at it area-wise. They're getting at it a little differently. Okay, so that's calculating the different situations for an exponential distribution. What I also want you to be able to do is convert this knowledge here to problems dealing with a Poisson. So you may be given a list of problems, and I do this for you in the notes. I give you a few exponential type problems, and then we switch to the Poisson. So now instead of this type of distribution with a lambda of 4, you now have a lambda of 4. You now have a distribution, a discrete probability distribution, where now the height of these bars are probabilities. There's no area here that we're interested in. So how do we deal with that? So let's say all of a sudden, besides being asked the amount of time that will lapse, let's say that we're asked, what's the probability 10 patients will arrive in the next minute? Well, you should see that as a very different problem, okay, than what was up here. This was the amount of time between arrivals. This is the amount of arrivals over a certain amount of time, in this case a minute. So what's the probability x will equal 10 arrivals per minute? And I just put a prime there to distinguish it from the x up here, the time x. This is the arrival x, number of arrival x's. And we just use the Poisson formula, so I'm not going to get into it. We did that in a previous video, the calculation, calculating the probability. You can also use the Poisson statement from Excel. Okay, so now this is on a per minute basis, and then this would be the cumulative. Instead of finding, if I wanted to do it with my formulas myself, I would have to do this for 0 up through 10 and add them up together. So I'm cheating here and using the Poisson statement, and in this case said true for the cumulative. Here, because it's discrete, when I say false, I get the actual probability. Okay, so I know it's a little confusing, but you just have to. This is why it's good to see the difference between exponential and Poisson. See the relationship as well as the difference, because one's continuous time, space, things like that, and one is a discrete number of arrivals. Now, if you were asked what's the probability that 10 patients will arrive over the next 5 minutes, then just make sure that you have the appropriate lambda. 4 is per minute, so you need to change your lambda to 20 for 5 minutes, and then you can find the probabilities based on that. So now you're still using x of 10, but now your lambda is 20. So you just have to be careful about that. And the same for up here, the amount of time. We could have changed this to seconds. We could have changed these to hours. And now, there's an assumption that you have to be careful with is that if you expand it, if it works for per minute, can you expand it to a per hour? Our assumption will be that you can, but depending on the particular situation, that may not always be the case. But in our problems, if I do change the time unit, the mean will adjust appropriately based on the time unit change. So if we went to per hour, then you would multiply this by 60. Since we're looking at 5 minutes, we multiply that by just 5. So be able to work out probabilities for both the exponential type statements and as well as the Poisson statements here. Know what you're dealing with, know whether you've got lambda or 1 over lambda, and if you have any questions about that, feel free to email me.